Okay, so we'll now start with the last talk of today. We're happy to have Sen Hu from Siemens, who will tell us about the large and limit of Chern-Simons matrix models and conformal field theory. Let's welcome him.
Okay, thank you. Yeah, thank you, the organizer, to invite me to give a talk. So I'm talking about Chern-Simons matrix model. And so we will use this model, we can derive conformal field theory. So there will be two approaches for Chern-Simons quantization of Chern-Simons matrix model. So one is canonical quantization, another one is geometric quantization. So we will use both. So in the deriving of conformal field theory, we rely on geometrical quantization. There should be similar things for the canonical quantization, but we have not finished that. So there are interesting problems in condensed matter, and all these interesting problems are connected with strongly coupled systems. For the Chern-Simons matrix model, they are useful to study fractional quantum Hall effect. So the theory was proposed by Laughlin for the wave function, and Houdan, and Susskind, and Polyhonkers. I think there are similar things for other condensed matter systems, like superconductor. So they were studied, the current theory is BCS theory, and also some theory proposed by Anderson and Peter Lee and Wen. So we hope matrix model can be used for this as well. So this can be Chern-Simons matrix model. It can be considered as an example to study this strongly coupled system. And so there will be emergent fields. The fields in this case, fractional quantum Hall effect, are actually fluctuations of density. And for superconductor, it will be fluctuations of charge density and hole density. And so to quantize this, the most important tool is to obey gauge symmetry and conformal symmetry, especially gauge symmetry in this case. This presentation rely on several works. That is the Chern-Simons large limit of Chern-Simons matrix model, and also previous work of Dorey and Tong and Turner. And for the geometric quantization, we are going to post this paper very soon. It's in the... So Chern-Simons matrix model was first proposed by Susskind, and it is infinitely many size matrix. So this matrix is difficult to quantize. And very soon, people construct a finite size matrix. So this is the action for the finite matrix. So this was proposed by Polyhonkers. So this is the Chern-Simons action. So Z n by n matrix, and A0. And so basically, you have Z dagger, and this is the covariant derivative with respect to T. And so lambda are the matter field. So it could be one vector or several combination of vectors. So that is, if one vector that gives, this is the matter field. So you have this S, abelian or non-abelian, depending on how many matters you have. So you can see it's very easy to see this action is invert and the conjugation of the matrix, and also the transformation of the fundamental field. So the action is, in this sense, is a gauge invariant. But this U, this UN matrix, shall not be considered as gauge symmetry of the matter. It's really kind of diffeomorphism symmetry, because they are acting on this Z matrix. So this matrix should be the analog of diffeomorphism symmetry. And if yes, also depend on T. Yes. Yes. Oh, sorry. Yes. So this should be, covariant derivative respect to T. Yes. Yeah, thank you. Yeah. So there should be another term, right? Okay. And so these are the covariant derivatives for A0 plus partial T. That is a covariant derivative. Yeah. And if you do variational equations respect to S0, so you have this condition. So this condition is the same as the moment map condition. So now you can do quantization. So we see there be two approaches in doing quantization. So one is the canonical quantization. So this is more familiar to physics. And for this, we have all the fields. We can quantize all these fields as non-interacting bosons. So you have all this quantum field. Each component can be considered as a boson. And you have the Fock space. But not all the vectors in this space are physical state. So physical state obey this gauge symmetry. So this will be invariant under this moment map condition. So this moment map forms UN algebra. So this constraint gives this UN symmetry. So now we can define, in this matrix model, we can define this quantum algebra. So the quantum algebra are simply generated by these operators. So this is like the Fock space. But now if you find a gauge invariant operator, so that is, it has to commute with the moment map condition. So this gives the UN invariant operator. But there are some operators that's internal. It's like modular exact term. So this term does not contribute to real observable. So if you modular this one, that gives the algebra of quantum observables. So they are the gauge invariant operators. The gauge means this UN symmetry. So these are the observables. So for example, there are two class of operators, gauge invariant operators. So if you, here it should be a trace. Not a trace, yeah. So here, if you symmetrize, you have this generating function, and you expand this, and you symmetrize this Z and Z diagram, and it's very easy to see. So they are gauge invariant operators. And so this is more like a Wilson loop operator. And you also can take a trace. You take a power of Z and Z dagger and symmetrize and take a trace. So that you give this phonos. So these two are an interesting class of gauge invariant operators. It's very clear they are gauge invariant because they take a trace. The commutative relations is not easy. Actually, this was first conjectured by Giotto 2 years ago. And he used Mathematica to calculate and guess this formula for the commutative relations. So last year we proved this this commutative relation by several methods. So first by hand, just calculate this. So later we found a better method to prove these commutative relations. So there are we can see there will be some lower degree terms. When I take a larger limit, this term will disappear. Only the terms left. And so this the term left will gives you Kac-Moody algebra. And this, so this algebra actually gave us Yangians. So I will explain this later. So first we have found this gauge invariant operators. And then you can also consider how this, you will find the physical state to construct the Hilbert space. So this Hilbert space will obey this condition. So the moment map acting on the physical state should be 0. So that gives you the gauge symmetry. And then we know that this is a U1 algebra. So it has U1 part and SU1. For the U1 part, it's simply this condition. So this condition means that you count the number of the physical state, you count the number of lambda I dagger. So that should be k times n. So this is kind of a constraint. That's the U1 condition. So this condition is more like this is an easy condition. And then you want to satisfy this SU1 invariant condition. So the physical state can be constructed as kind of a tensor. SU1 invariant tensor. So that means you have this antisymmetric tensor with this product. So you have lambda and z. If you have all these creation operators, so these operators, that should be a vacuum. So this operator you add on the vacuum. And all these are commutative. So that does not matter, you have the position. But they should be SU1 invariant. So you have this invariant tensor, this will be SU1 invariant. So that is the typical physical state. And you can also calculate the energy of this state. Then you can find the ground state. Yeah. So the ground state, you have the number of powers, the lowest as possible. So that gives you the ground state. Because this cannot be the same. If they are the same, you have this antisymmetric tensor, that be 0. So this is the lowest state with the lowest energy. So that is the ground state. But if you, this is for P1, actually this ground state corresponds to the Laughlin wave function. And if you consider more a non-abelian case, so the ground state you need to have this Young diagram to specify the ground state. So for p equal to 1, you can write down this. Okay, so that gives you the quantization for using canonical quantization. So now if we consider, we take a larger limit. So take a larger limit, we can consider as take a larger limit of the algebra. So this algebra, you consider take a larger limit. You cannot do it straightforward, because if you consider n by n matrix, the identity matrix, so the size of n plus 1, you cannot identify this one with n by n. Yeah, you miss 0, so they cannot be identified. So you cannot do it in a straightforward way. We can do this because we have this commutator relations, and this commutator relations is independent of n, capital N. So this way we can generate these operators and subject to these relations. So we can define this algebra explicitly using these commutator relations, because they are, the relations are independent of n. So this way we can define, we call the uniform in n algebra. So you have this, so the sequence of these operators, and you consider this sequence of these operators as element in this uniform n algebra. So this way we define the larger limit of observables. So this sequence gives you a larger limit. And when we do this, construct this representation, we need to rescale this operator. Otherwise, we are not converged. So this is the rescaling factor. Actually, the rescaling, you have this factor. Largely, you have capital N. So the factor depends on the index. So we can rescale these operators, and then we take a larger limit. So when you do this, you will find that a lot of lower order terms will disappear. You only have the main terms. Actually, the main term, this one will obey this Kac-Moody algebra relation. So this gives you this current algebra. And for this one, you also have this phonos. We have this phonos as well. So this algebra is actually the quantum observables in the larger limit. So originally you have 2 index, but you can degenerate. You only consider difference of the index. So that will gives you Kac-Moody algebra, right? And also this phonos. So we can do this in an abstract way, but when we consider representations, so this degeneration actually appeared automatically. So in the representation of the larger limit, so this 2 index becomes 1 index automatically. Okay, so here is the Hilbert space. So this is the basis of the Hilbert space. So take a ground state and you use these phonons and acting on this ground state. So that gives the basis. And then from your basis, you can construct two operators. So one is called a creation operator. So Ci, you take a power Ci to Ci plus 1. And you can also consider annihilation operator. So you decrease by 1. Actually, these two operators are similar as Nakajima's operator in these Hilbert schemes. So from the geometric connotation, you can see very clearly they are the same. So then using this, so you have this Hilbert space would be the polynomials of these variables. So now if you want to consider representations of this algebra over on the Hilbert space. So first you have this basis, and then you need to calculate the generators acting on the basis. So for example, you have this one. So that you can calculate, we have this called graphical calculus. So using diagrams to represent the state and also operators. So you can calculate this. So this, you can, after this graphical calculus, you can see that it be represented by these Nakajima's operators. So that can be calculated directly. And you can also calculate a few more, T10 and T21, T11 and T21, T12. So you calculate this. So then you use these relations. You calculate all the operators acting on the Hilbert space. Then we found that the repetitions of this operator on the Hilbert space only depend on the difference of index. So they're actually represented by these Nakajima operators. So they degenerate into this Kac-Moody algebra. Okay, so that is the first approach using canonical connotation. So now I will come to the second one, the geometrical event theory, the geometrical connotation. So this connotation should be considered equivalent to the first one, but it has need more mathematics. But actually, this approach, so when we have this some basic concept, so this approach is much easier than the first one. So for the geometrical connotation, so we use geometrical event theory. So the canonical connotation, we have seen this model space, this matrix, obey this Gaussian constraint. And from geometrical event theory, so this model space is the same as the matrix and also the map from subspace to the big space. And satisfy this we call the stability condition. So the lambda is a map from the subspace into the big space. It's like a matter field. So this matter field, you have this matrix and also the power of the matrix. These are the polynomials of Z acting on the image. Will generate the whole space. So this is the stability condition. So the model space in this case is modified to a space satisfy this stability condition. And also you use conjugation. So this model space is much easier to study than using this one because this is a constraint. you always have this constraint. And this condition is an open condition. So you only need to delete some unstable point. Yes. 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 No, so here is the classical modular space. So we need to have this line bundle. So no. Yeah, not say from here. Yes. Yeah. So this modular space is actually isomorphic to people call the code scheme from algebra geometry. So these are the affine line parameterizing a less n finite quotients. So here you have this line bundle over A1. So A1, so we see, so they have this CZ here. So you can see the spectral parameter appeared if you use complex variable. And so here we have this A1. So now you have this bundle, the line bundle over here. So you take a final sum, p sum of this vector bundle. So the code scheme is a little bit abstract. Actually, it is kind of a bundle over the some Riemann surface. So you define this. So you have this one, and you have this map, and so the kernel determines a bundle. And so for this bundle, actually this is this bundle. You also have a divisor associated to this bundle. So this is called a Hilbert Chern map. So you map a bundle to its divisor. So this is a little bit abstract, but we can use we call affine Grassmanni to make this more concrete. So you have this bundle and have the divisor. And so this is we call affine Grassmanni. So on each divisor, you can specify some local sections, some degree. And you have some, it's like the information of the divisor. So that gives you the affine Grassmanni. So the model space in this case are really affine Grassmanni. And in this affine Grassmanni, there's a canonical line bundle, we call it determinant bundle. So this determinant bundle can be defined as well. You have this bundle, you can consider quotient bundle and consider determinant. So that gives a line bundle over the affine Grassmanni. So then a Hilbert space would be holomorphic sections of this affine Grassmanni. So this is a geometrical quantization. So the definition looks more complicated so than a canonical quantization. But however, it's much easier to study to this space rather than this canonical quantization, Hilbert space. Okay. So now we can define, again, we define this algebra. So we call the deform, this actually was, we defined this before. you have is generated by this element. So the phonemes and various loops and two central elements. So this algebra we call AP. So this algebra, that's a very natural map, a canonical map, we call it skew linear anti-evolution. It's like to take a joint. So take a joint, you can also have this inner product of the Hilbert space. So this we can show actually the Hilbert space we constructed is a simple module of this algebra. This is called deformed double current algebra. The interesting thing is in this algebra, we can define a subalgebra, so generated by this generating function. So this subalgebra actually gives us a Youngins. It's a Youngin subalgebra. Because you consider this and you calculate, you expand as a component, so that you calculate this. They satisfy this RTT relation. So this gives us a Youngin subalgebra. In this Youngin algebra is also commute with T11. So we can calculate this directly. From this condition, that means so the Hilbert space can each energy level of the same energy will be a Youngin submodule. So altogether, so we found that the Hilbert space we constructed is really a unitary module representation of the Youngins. So this was proposed by Haldane and his collaborator in the 1990s to study this spin chain. So because it is satisfy this relation, you will derive this Yang-Baxter relation automatically. So this way, Haldane, they consider since they have found this Youngin algebra, and the spin chain can be considered as a highest rate representation of the Youngins. So you can solve this model directly. So the algebra of Youngin is the key to solve the spin chain. So also it can be explained here. So that is representation of Youngin. So if you go a little bit further, you have this Yang-Baxter relation, you have the Betz ansatz, all appear automatically. Okay, so now we can make this more explicit. So before I give you abstract definition, but if you want to see the wave function and all these operators explicitly, so it's better they have two matrices, Z and Z diagonal. So you can use this conjugation to diagonalize the first matrix. So then it becomes a diagonal matrix. And then you, the matter fields, you use this as the remaining variables of matter field. So this, when you diagonalize, so the eigenvalues can be considered as the positions of the electrons. And then if you consider the wave function, so that will depend on x and y. So since they are SON invariant, and also you have the local gauge symmetry. So the wave function if you fix this xi, that should be the homogeneous polynomials. in this Y. Actually, if you diagonalize this and you write this Z dagger as this moment operators, so we will see they are actually spin chain, give you a spin chain. So the wave function depend on Y and X. So these are the positions, and Y are the matter field. So in the matter field, they should be homogeneous polynomials, symmetric polynomials. So that gives you a wave function. Actually, this wave function coming from the ground state we have constructed before using this SUN in one tensor. So now if you diagonalize this, you will see that this wave function is actually determinate. So this is for k equal to 1, if you consider k equal to 3. So that gives you the Laughlin wave function. And and all the algebra, the operators, if you have diagonalized the first one, we call this a Kac-Moody representation. And then all the gauge invariant operators can be represented by differential operators. So these differential operators actually gives you the Hamiltonian of the spin chain. So this operator depends on the quadratic Casimir. And using this, we can reconstruct this Hamiltonian. And this Hamiltonian so commute with this Youngins. So that's why we have this the Hilbert space is the representation of this Youngins. So that I explain. Well, these are all the direct calculations. Yeah. So from as long as you have this, they are the symmetries of the Hamiltonians, the spin chain. So that's why these Youngins are the symmetries of the spin chain. So that explains this work of Holden. Yeah, so using this, you make everything explicit. So all the operators can be written down using this differential operators. So now we can define this conformal block. So our goal is to derive conformal field theory out of this matrix model. So the key, so there are several factors. So you have this modular space. And so when you diagonalize the first matrix, you have this eigenvalues. So this like X. And if you fix X, you have this Y's. And this Y, you can, the fiber, in that fiber, you can also have this line bundle and consider holomorphic sections of this line bundle. And we can calculate this. So this space are actually the module of the current algebra and phonons. So this we call this, so this a dual space. So if a dual again, that becomes dual here. So we call this a conformal block. So if you fix the positions of X and the fiber, you have the modular space, and you do the quantization. Actually, this is the Hilbert space. So this give you the module of this current algebra. So that gives you the conformal block. So this conformal block is invariant under this algebra. So when we see we have the conformal field theory, it's really for each fiber you have the Hilbert space. And this Hilbert space is fibered over this space, the positions of X. So to have a conformal block means we will construct a flat connection, project flat connection over this space. So this space is like a modular space of Riemann surface. So each one you have this Hilbert space. This is like a vector bundle. You have construct real conformal block, conformal field theory, you need to construct a flat connection of this bundle. So this we call the Kac-Moody equation. Actually, so this flat connection appeared very naturally from the construction. Because each fiber, it admits D-module structure. It's really equipped with a flat connection. That's also, yeah, I delete one before. So actually this flat connection coming from the Hilbert-Chern map is flat. So it's a very abstract theorem in algebra geometry. As a consequence, you can construct a flat connection. And this flat connection, if you use this Caligari representation, we can write down explicitly. So this is by abstract result, we have this flat connection. And then you use this Caligari representation. So you can write down this flat connection explicitly. So this, in this coordinate, they are actually the same as the Kac-Moody equation. So this way we show that this wave function obey this Kac-Moody equation. And they are the conformal blocks, not only on fiber, but also depend on the modular space as the sections of the modular space. So we have construct this conformal block and obeys Kac-Moody equation. This way we see we can derive this conformal field theory. Okay, thank you. Yeah.
Do we have any questions?
Thanks for the talk.
Yeah.
Is it possible, my question is it possible to construct some kind of correlation functions appears in
Yes, that's a very good question. Actually, so this is possible. So to calculate the correlation function is to calculate the inner product of the Hilbert space. And using our graphical calculus, we can calculate this correlation function as well.
Yes, is
Yes.
it possible to get some version of some matrix version of the correlation functions appears in the say non-abelian Chern-Simons non-abelian Chern-Simons series, say the Lofting function or the Moreid function?
Yeah. It's, so we have the tool to calculate this, but we have not done enough calculation. Yeah.
Okay, thanks.
Yeah, simply the inner product of the state. Yeah.
Any more questions?
Yeah. So partition function can also be calculated. Yes, both for abelian and non-abelian.
Okay, if there are no more questions, let's thank Professor Hu again.
Okay.